transformer kilovolt-ampere ratings have some consistency across utilities. The National Electrical Manufacturers Association, or NEMA, outlines standard kilovolt-ampere ratings for distribution transformers that include 300 kV, 500 kV, 750 kV, 1000 kV, 1500 kV, and 2000 kV. However, utilities might use transformers with different kilovolt-ampere ratings depending on specific load requirements and distribution system configurations. A utility transformer's impedance isn't directly related to its kilovolt-ampere rating. The transformer's design and construction determines impedance, including the number of turns on the primary and secondary windings, the core material, and insulation. Variations in impedance values are likely due to several factors. Firstly, transformer design and manufacturer differences can cause variations in impedance values, as different manufacturers might use different designs and materials. Secondly, the age of a transformer can influence impedance, with older transformers potentially having higher impedance values because of deterioration over time. Thirdly, measurement methods can impact the reported impedance value. Fourthly, utilities might have specific impedance requirements for their distribution systems, leading to different values for transformers in different locations. To obtain accurate impedance data for a specific transformer, firstly, request the information from the utility company. Secondly, if the utility cannot provide the data, consider hiring a qualified electrical engineer to perform impedance testing. Thirdly, when calculating maximum available fault currents, use conservative impedance values. Transformer impedance values vary depending on design, manufacturer, age, and measurement methods. While some consistency exists in kilovolt-ampere ratings, utilities may use transformers with different impedance values. Getting accurate impedance data from reliable sources is important for ensuring proper electrical system design and safety. Short-circuit current depends heavily on the impedance values of the main utility transformer. In an installation with a short main feeder, the utility transformer may be the only thing between a switchgear and the entire output of a dam, ending up in an arcing fault in an electrical closet. Impedance is a measure of opposition to alternating current, similar to resistance in direct current circuits, but also taking into account the effects of inductance and capacitance. Transformer impedance is expressed as a percentage. This percentage represents the voltage drop across the transformer when it is fully loaded. A lower impedance percentage means a higher potential fault current, while a higher impedance percentage limits the fault current. There are a few reasons for variations in transformer impedance. Firstly, transformer design differences across manufacturers can lead to impedance variations. Secondly, the transformer's age can affect impedance because older transformers may have higher impedance due to winding insulation degradation and core aging. Thirdly, different measurement methods can lead to variations in reported impedance values. The method used to measure transformer impedance can impact the reported value. Utilities may also have specific impedance requirements for their distribution systems, leading to different values for transformers in different locations. Obtaining accurate impedance data is vital for proper electrical system design and safety. Request the information from the utility company, as they are the primary source of this data. If the utility cannot provide the data, consider hiring a qualified electrical engineer to perform impedance testing. Use conservative impedance values when calculating maximum available fault currents to ensure safe design. Regarding the question about wildly different values of impedance for utility transformers from different sources, and the mention of the Busman EDP-1 handbook, along with varying percentages from different sources such as the 1984 edition listing impedance of a 300 kV amp utility transformer as 1.14% resistance, 4.0% reactance, 4.16% impedance, a newer version online listing the same transformer as 1.2% impedance, and the latest utility listing the 300 kV amp transformer as 2.5% impedance, resulting in varying maximum available symmetrical fault current between 8,600 and 30,000 amps. These variations highlight the importance of obtaining accurate and up-to-date information for specific transformers in a particular installation. Relying on outdated or generic data can lead to significant errors in fault current calculations, potentially compromising the safety and reliability of the electrical system. There are several factors contributing to these discrepancies. Firstly, the design and construction of the transformer, as each manufacturer may employ different design parameters, materials, and manufacturing processes, resulting in variations in impedance. Secondly, the age and condition of the transformer, because as transformers age, the insulation and core materials can degrade, leading to changes in impedance values. Thirdly, variations in utility specifications are often seen, because utilities may have specific requirements for transformer impedance to maintain system stability and coordination, leading to differences in transformer specifications from different utilities. The most reliable method for obtaining accurate impedance data is to directly request it from the utility company that owns and operates the transformer. This data should be specific to the transformer serving the installation and should reflect its current condition. If direct data is unavailable, consider hiring a qualified electrical engineer to perform on-site impedance testing. These tests can provide accurate impedance values specific to the transformer in question. When calculating fault currents, it's essential to use conservative values for impedance to ensure that the electrical system is adequately protected. This means using the highest impedance value within a reasonable range of uncertainty to account for potential variations. There are standards that dictate transformer construction. The Institute of Electrical and Electronics Engineers, or IEE, is a professional organization that develops standards for various aspects of electrical engineering, including transformers. IEE Standard C57.12.0 covers general requirements for liquid immersed distribution, power, and regulating transformers. IEE Standard C57.12.90 covers test procedures for liquid immersed distribution, power, and regulating transformers. The American National Standards Institute, or ANSI, is a non-profit organization that coordinates the development and use of voluntary consensus standards in the United States. ANSI approves standards developed by organizations like IEE and NEMA. The National Electrical Code, or NEC, provides guidelines for the safe installation of electrical wiring and equipment. While the NEC doesn't directly specify transformer construction standards, it references other standards such as those developed by IEE and NEMA. The International Electrotechnical Commission, or IEC, is a global organization that develops international standards for electrical, electronic, and related technologies. IEC standards are often adopted or adapted by national standards organizations. The transformer's nameplate provides important information about the transformer's characteristics, including its kilovolt-ampere rating, voltage ratings, impedance, and other relevant parameters. This information is crucial for proper application and operation of the transformer. Understanding the nameplate is crucial. Firstly, the kilovolt-ampere rating is the apparent power that the transformer can deliver at its rated voltage and current without exceeding its temperature limits. Secondly, the voltage ratings are the primary and secondary voltages for which the transformer is designed. Thirdly, the impedance is the percentage of the transformer's rated voltage that must be applied to the primary winding to cause rated current to flow in the secondary winding when the secondary winding is short-circuited. Fourthly, the frequency is the frequency for which the transformer is designed, typically 60 Hz in North America. Fifthly, the number of phases indicate whether the transformer is single-phase or three-phase. Sixthly, the insulation class is the maximum temperature that the transformer's insulation can withstand without degradation. Seventhly, the cooling method is the method used to cool the transformer, such as oil filled with natural convection, oil filled with forced air, or dry type with natural convection. Variations in transformer impedance values can arise from several factors. Firstly, manufacturing tolerances, because transformers are manufactured to certain tolerances, and variations within these tolerances can lead to differences in impedance values. Secondly, tap settings, because some transformers have tap settings that allow for adjusting the voltage ratio. Changing the tap setting can affect the impedance of the transformer. Thirdly, temperature variations, because the impedance of a transformer can vary with temperature. As the transformer heats up, the impedance may increase. Fourthly, core material, because the type of core material used in the transformer can affect its impedance. Different core materials have different magnetic properties, which can influence impedance. Fifthly, winding configuration, because the way the windings are configured in the transformer can affect its impedance. Different winding configurations have different impedance characteristics. When selecting a transformer, consider several factors, including the load requirements, voltage levels, impedance, and applicable standards. Accurately assess the load requirements. This includes determining the kilovolt-ampere rating, voltage levels, and any special load characteristics. Select a transformer with an appropriate kilovolt-ampere rating and voltage levels to meet the load requirements. Review the transformer's impedance. The impedance should be suitable for the application and should be coordinated with the electrical system's protective devices. Ensure that the transformer complies with applicable standards such as those developed by IEEE, ANSI, and NEMA. In summary, variations in utility transformer impedance values can arise from several factors, including manufacturing tolerances, tap settings, temperature variations, core material, and winding configuration. When selecting a transformer, consider the load requirements, voltage levels, impedance, and applicable standards to ensure proper performance and safety. Regarding the calculation of fault current, firstly determine the transformer's impedance. Obtain the transformer's impedance from the nameplate or from the utility company. Convert the percentage impedance to per unit impedance by dividing the percentage impedance by 100. Secondly, determine the transformer's kilovolt-ampere rating. Obtain the transformer's kilovolt-ampere rating from the nameplate. Convert the kilovolt-ampere rating to volt-amperes by multiplying the kilovolt-ampere rating by 1000. Thirdly, calculate the transformer's full load current. Divide the transformer's volt-ampere rating by the secondary voltage to obtain the full load current. Fourthly, calculate the fault current. Divide the full load current by the per unit impedance to obtain the fault current. The resulting fault current represents the symmetrical fault current at the secondary terminals of the transformer. This value is used to determine the appropriate interrupting rating for circuit breakers and fuses. The available fault current is the maximum current that can flow in a short circuit. It is limited by the impedance of the power source, the conductors, and the equipment in the circuit. The available fault current is an important factor to consider when selecting electrical equipment. Electrical equipment must be able to withstand the available fault current without being damaged. The interrupting rating of a circuit breaker or fuse must be greater than or equal to the available fault current at the point where it is installed. The short circuit current rating, or SCCR, is the maximum fault current that a component or assembly can safely withstand. The SCCR of a component or assembly must be greater than or equal to the available fault current at the point where it is installed. A short circuit is an abnormal condition in an electrical circuit where current flows through an unintended path with very low impedance. This can be caused by insulation failure, accidental contact between conductors, or equipment malfunction. Short circuits can result in high currents, overheating, arcing, and potential damage to equipment and injury to personnel. Protective devices, such as circuit breakers and fuses, are used to interrupt short circuits and protect electrical systems. When a short circuit occurs, the protective device quickly detects the high current and opens the circuit, preventing further damage. Proper coordination of protective devices is essential to ensure that the device closest to the fault interrupts the circuit, minimizing the impact of the short circuit. Consider overcurrent protection. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from excessive current. Overcurrent can be caused by overloads, short circuits, or ground faults. Overcurrent protection devices are rated in amps and have an interrupting rating, which is the maximum current that the device can safely interrupt. Electrical systems must be designed with appropriate overcurrent protection to prevent damage to equipment and injury to personnel. Consider the coordination studies to ensure the system has them. Coordination studies are performed to determine the optimal settings for overcurrent protection devices in an electrical system. The goal of coordination is to ensure that the device closest to the fault interrupts the circuit, minimizing the impact of the fault. Coordination studies involve analyzing the electrical system's impedance, fault currents, and device characteristics. The results of the coordination study are used to set the time current curves of the overcurrent protection devices. Performing coordination studies is essential for ensuring the reliability and safety of electrical systems. It is important to obtain accurate impedance data from reliable sources to ensure proper electrical system design and safety. Regarding the quick and dirty calculator available online, it is essential to recognize that online calculators provide approximations. These tools use simplified models and assumptions that might not fully represent the complexities of real-world electrical systems. While online calculators can be useful for preliminary estimates and quick assessments, it's crucial to validate the results with more detailed calculations and engineering analysis. When using online calculators, understand the limitations of the tool. Be aware of the assumptions and simplifications made by the calculator and how they might affect the accuracy of the results. Use the calculator's output as a starting point. Use the results from the online calculator as a starting point for more detailed calculations and engineering analysis. This may involve using more sophisticated software tools, consulting with a qualified electrical engineer, or performing on-site measurements. Verify the results with other sources. Compare the results from the online calculator with data from other sources such as transformer nameplates, utility company data, and engineering studies. This can help identify any discrepancies or errors in the calculator's output. In summary, online calculators can be useful tools for estimating fault currents and other electrical parameters. However, it's essential to recognize their limitations and validate the results with more detailed calculations and engineering analysis. Don't rely solely on online calculators for critical decisions related to electrical system design and safety. It is important to use them as a supplement to, not a replacement for, sound engineering judgment and analysis.